Selecting the appropriate wire gauge and conduit size for a commercial electrical installation is critical for safety and performance. In this specific scenario, there are 4 NML14-30 receptacles, each requiring 2 hots, 1 neutral, and a ground, totaling 13 conductors within a single conduit over a 200-foot distance from a 3-phase panel operating at 208 volts alternating current. The loads are UPS units drawing 22 amps continuously. Because the neutrals carry current from the loads, they are counted as current-carrying conductors. Let's delve into the calculations and considerations for determining the correct wire gauge and conduit size. Firstly, understanding the impact of neutrals in a 3-phase system is paramount. In a balanced 3-phase system, the neutral conductor ideally carries minimal current, as the currents from each phase cancel each other out. However, in this situation, the neutrals are specified for each receptacle independently due to the nature of the loads, which are UPS units, and also for potential future expansion. Since each receptacle has its own neutral, and the loads are not perfectly balanced, the neutrals will carry current and therefore must be counted as current-carrying conductors. Secondly, conduit fill calculations determine the appropriate conduit size to accommodate the number of conductors. Formula for conduit fill percentage is the area of conductors divided by the area of the conduit. For 13 number 6 THHN wires, the calculation must ensure the conduit fill does not exceed the maximum allowable percentage as specified by the National Electrical Code. The area of a single number 6 THHN wire is approximately 0.817 square inches, or 5.261 square millimeters. A 2.5-inch conduit has an internal area of approximately 3.14 square inches, or 4,908.0 square millimeters. Conduit fill percentage equals 13 times 5.261 square millimeters divided by 4,908.0 square millimeters, resulting in approximately 13.8%. This is significantly below the 40% maximum fill allowed by the NEC for multiple conductors in a conduit. Therefore, a 2.5-inch conduit is sufficient. Thirdly, determining the appropriate wire gauge involves considering ampacity and voltage drop. Ampacity refers to the current carrying capacity of a conductor, which is dictated by the wire gauge and insulation type. For a 30 amp circuit, as specified by the NEM L14-30 receptacles, the minimum wire gauge must be sufficient to handle this current continuously. Number 10 AWG copper wire is typically rated for 30 amps at 90 degrees Celsius, but this is the starting point. Voltage drop is the reduction in voltage along the length of the conductor due to its resistance. Excessive voltage drop can cause equipment malfunction and inefficiency. Acceptable voltage drop is typically limited to 3% for branch circuits. The voltage drop can be calculated using the formula voltage drop equals 2 times K times I times D divided by Cm, where K is the constant for copper, approximately 12.9 ohms circular mils per foot, I is the current in amps, D is the one-way distance in feet, and Cm is the circular mils of the wire. For a 208-volt circuit with a 22 amp load over 200 feet, the voltage drop calculation is as follows. For number 10 AWG wire, which has a circular mil area of 10,380, the voltage drop equals 2 times 12.9 times 22 times 200 divided by 10,380, which equals approximately 10.98 volts. The percentage voltage drop equals 10.98 volts divided by 208 volts, which equals approximately 5.3%. This exceeds the 3% limit, indicating that number 10 AWG wire is insufficient. For number 8 AWG wire, which has a circular mil area of 16,510, the voltage drop equals 2 times 12.9 times 22 times 200 divided by 16,510, which equals approximately 6.88 volts. The percentage voltage drop equals 6.88 volts divided by 208 volts, which equals approximately 3.3%. This is still slightly above the 3% limit. For number 6 AWG wire, which has a circular mil area of 26,000 240, the voltage drop equals 2 times 12.9 times 22 times 200 divided by 26,240, which equals approximately 4.33 volts. The percentage voltage drop equals 4.33 volts divided by 208 volts, which equals approximately 2.1%. This is well within the 3% limit. Considering the 100% load factor, which means the UPS units will be loaded to 22 amps continuously, it is imperative to select a wire gauge that can handle this continuous load without overheating. The National Electrical Code Article 210.19 A1 states the branch circuit conductor shall have an ampacity not less than 125% of the continuous load. Therefore, the conductor must be rated for at least 1.25 times 22 amps, which equals 27.5 amps. Number 10 AWG wire is rated for 30 amps, but given the voltage drop considerations, it is not suitable. Number 6 AWG wire, rated for 55 amps at 90 degrees Celsius, easily meets this requirement. Fourthly, temperature rating and deterring factors must be considered. The THHN wire is rated for 90 degrees Celsius. However, the ampacity of the wire must be derated if it is installed in a conduit with multiple current carrying conductors, especially in environments where the ambient temperature is high. AEC Table 310.15. B3. I provide adjustment factors for the number of current carrying conductors in a raceway or cable. With 13 current carrying conductors, the ampacity of the wire must be derated to 50% of its original value. For number 6 AWG THHN wire, the ampacity after derating is 55 amps times 0.5, which equals 27.5 amps. This is precisely the minimum ampacity required for the continuous load, leaving no margin for error. To provide a safety margin and account for any unforeseen factors, it may be prudent to consider using a larger wire gauge such as number 4 AWG, which has an ampacity of 70 amps at 90 degrees Celsius. After derating, the ampacity would be 35 amps, providing a comfortable margin above the required 27.5 amps. However, this would also increase the conduit fill, so that must be re-evaluated. Fifthly, grounding considerations are essential for safety. A separate grounding conductor must be included in the conduit to provide a low impedance path for fault current to return to the source, tripping the circuit breaker and preventing electrical shock hazards. The size of the grounding conductor is typically based on the size of the ungrounded conductors, as specified in NEC Table 250.122. For number 6 AWG conductors, a number 10 AWG grounding conductor is generally sufficient. 6. NEC compliance is paramount. All wire gauge and conduit size selections must comply with the latest edition of the National Electrical Code. The NEC provides detailed guidelines for conductor ampacity, voltage drop, conduit fill, and grounding. It is essential to consult the NEC and any applicable local codes to ensure that the installation meets all requirements. In conclusion, based on the calculations and considerations, number 6 AWG THHN wire in a 2.5-inch conduit is a reasonable choice. However, given the continuous load, derating factors, and desire for a safety margin, number 4 AWG wire may be a more prudent option. It is crucial to verify all calculations and selections with a qualified electrical engineer or licensed electrician to ensure compliance with the NEC and local codes. Additionally, the specific conditions of the installation, such as ambient temperature and load characteristics, should be carefully considered. It's important to note that while the calculations provide a solid foundation, a professional electrician will perform a thorough on-site assessment to account for any unique factors. Always prioritize safety and adherence to electrical codes.